Hello and welcome. In this video, we would start talking about stochastic processes. Okay. And when I talk about stochastic processes, I'll talk about them in light of the objective of the subject. Okay. And the objective of the subject is to create models for a real life process. And that's what our objective would be with this chapter as well. So what I would try to do here is I would try to discuss a particular type of processes that are called as stochastic processes, and then I would try to detail on how to model them or what may be the different types of stochastic processes that we may be dealing with. To take a formal definition, a stochastic process is a time dependent random phenomenon. So it can be any time dependent random phenomenon. The best example is, say you are tracking the price of a stock in the stock market. Okay. For example, you're tracking the price of a stock of, if I talk about the Indian context, you're tracking the stock price of Infosys. Now this stock price, it is a random phenomena and it is time dependent. Let's see how. If you're checking the price at the end of every day, that is the closing price. Okay. You can have a particular price of, let's say, maybe 1,000 on the first day. Okay. On the second day's end, you may have a price of 998 and so on and so forth, right? You can have different prices and they're changing with time. And you do not know what the price would be tomorrow, right? So it is a random phenomena. It is taking random values and it is time dependent. Okay. So this is a very good example of a stochastic process. Okay. And a lot of people try to model these stock prices in the stock market, and they try to predict these prices using technical and fundamental analysis. Okay. So it is something which can be predicted and modeled as well. Okay. So it is a very good example, and we talk more about stock market prices and everything in subject CT8, right? So that is one good example you can take. Another example for a time dependent random phenomena can be a very good example is what you have already studied in subject CT1. When I say the word stochastic, the first thing that comes to your mind is stochastic interest rate models that you studied in subject CT1. Okay, so what used to happen in subject CT1 is that when you had your interest rate, okay, in the first 14 chapters of CT1, you had been assuming it to be a constant rate. You had been assuming that the interest rate was deterministic. That if it is decided at 5% once, it would remain 5% throughout the life of the contract, right? But in the last chapter that was related to stochastic interest rate models, the assumptions changed. And they changed how? See, in there what used to happen was that you had different interest rates for different years. So you could have a different interest rate at time 0. So this is maybe time, and this is the interest rate. So you had an interest rate that was I0 and a different interest rate at I first year and an interest rate at second year. You know, you had various interest rate which were operating in different years, and for each of the interest rate you had their distributions given. Okay, and in CT1 we used to assume that these interest rates are IIDs, that are they're independent and identically distributed. So what we used to do was we used to have for any IT we used to have a distribution. For example, it could be 6% with a probability of 20%. It could be 7% with a probability of 30%, and then it could be 8% with a probability of 0.5. Okay, so it had a distribution. Okay, so here when we had a random phenomena, we used to model it as a random variable with which can change with time, right? And that is what we'll be doing here as well. Okay, so I've written that a stochastic process is a time dependent random phenomenon, and it can be modeled as a set of ordered random variables xt. So an example of this was, as we did in case of interest rate, I0, I1, I2 going up till IT. Okay. Here also I was modeling these interest rate as random variables. Okay. So any random variable can be these are different random variables which are changing with time. So I0 is a separate random variable, I1 is a separate random variable, I2 is a separate random variable, so on and so forth. Okay. So it's a set of ordered random variables, and they can have different distributions. Although in CT1 we assumed that they were independent and identically distributed. That is, their distributions were independent of each other and they were the same for all the interest rates. But that might not be the case, right? So it is possible that they can be they can have different distributions. So you can look at these random variables as different. You can look at a stochastic process as different random variables which are ordered by time. Okay, so that is how it is represented. So with the stochastic process, we have an ordered set of random variables defined at different points of time. Okay. So for example, at time 0, a random variable, our stochastic process can be x0, that is one random variable. And at time 1, you can have another random variable, that is x1. And at time 2, you can have another random variable, that is x2. So these are all random variables and they're ordered by time, right? So you can think of it this way, that a stochastic process is a function of time. Okay, it is xt, where xt is a function of time, right? It's a function of time. So when I talk about functions, there is an independent variable and a dependent variable, right? We used to have y is equal to fx, okay, usually. And all the possible values of y were in a set which was called as range. Okay, so range was the set of all the possible values that our dependent variable could take, and all the possible values of x are in a set which are called as domain, right? Similarly, for stochastic processes we have a similar nomenclature. Since xt is the dependent variable here and time is the independent variable, all the values which are taken by t, or that is at all the times at which xt is defined, okay, these are in a set which is called as time domain, or it's also called as time set, right? And it is denoted by a letter j. Okay, and all the values which each xt can take, okay, all the possible values which each xt can take are in a set which is called as state space, which is denoted by the letter capital S. Okay, so if I see for all my examples here, so if I see for this interest rate model I had here, interest rates were independent and identically distributed. Okay, and they had this distribution: 6%, 7%, and 8% with these probabilities, right? So this was all the values of I, and this was the probability that I was equal to a particular interest rate, right? Okay, so you had this distribution for I, right? So now if I talk about it, see, these are all the possible values that I can take: 6%, 7%, and 8%. So your state space becomes 6%, 7%, and 8%. It contains all the possible values that the random variables can take, okay, at any point of time. And your time set becomes all the times at which this random variable of interest is defined. So it becomes 0, 1, 2, 3, so on and so forth, right? So it is all the times at which this random variable of interest is defined, and then the state space is the set of all possible values that this random variable can take, right? So that is a valid example for this. And if I talk about the stock price of Infosys here, okay, see, this stock price, it can take any value between 0 to infinity, right? There's no limit on it. Okay, it can even take decimal values, right? So the state space becomes 0 to infinity. Okay, and the time set, if I talk about the time set, okay, the price of this stock is defined at all points of time. So it is continuous. It is defined at in a continuous interval. So the time set also becomes from 0 to infinity, right? So that is my time set here. But then if I'm checking the prices at the end of each day, if I'm checking the prices at the end of each day, that is the closing prices for the day, then my time set changes a bit. Okay, it can be at the end of day 1, or it can be at the end of day 2 or 3, or so on and so forth. So in that case, my time set becomes this. So what we effectively see using these examples is that my time set and my state space, both of them can be discrete as well as continuous. Okay, they can either be continuous, that is, they can take a range of values, or they can be discrete, right? So all the values, they can be in an interval. For example, our stock market prices, they were in an interval 0 to infinity, right? And our interest rates were discrete. They took a fixed set of values, so they could be 6%, 7%, or 8%, right? Right, 6%, 7%, or 8%. So this was an example of a discrete state space. Okay. And when I talk about time set, they can either be defined at discrete points of time. Okay. They can take possible values at discrete points of time, or they can have their values which are defined at every moment. So they can have continuous definition as well. So this could have been 0 to infinity in case of when the interest, when the stock market price was tracked throughout the day or throughout a year. Okay, so it can change at every moment. But then if you're checking day end prices, it can be discrete as well. So in that case, it could be defined at the end of day 1 or day 2 or day 3 or so on and so forth, right? So both the state space and the time domain can be continuous or discrete, right? That is to be noted. So based on the state space and the time domain, there is a four-way categorization of stochastic processes. Okay. So how does that function? See, you can have processes which have a discrete state space and a discrete time domain, right? And then you can have, continuous here as well. So you can have a continuous time domain and a continuous state space as well. Okay, so that gives me the four types. There can be ones with a discrete state space and discrete time domain, discrete time domain and continuous state space, continuous time domain and discrete state space, and continuous case, right? So you can have this four-way categorization here. Okay, and let's take example of each one of these. Okay, now this these examples, they are not exhaustive. There can be other examples as well, but I'm concentrating on a few which we would be studying throughout this subject, or which we'll be dealing with later. Okay, so for the discrete state space and the discrete time set process, the most common example is a no claim discount scheme. Okay, no claim discount. This is also referred to as NCD, right? Now let's try to understand what an NCD model is. Okay, no claim discount. Now what happens in, see, this is basically related to general insurance. To understand this better, let's take an example of a particular general insurance, that is automotive insurance. Now what happens in automotive insurance is that they are 1-year contracts like any other general insurance contract. And whenever you have an accident and you have a loss to your vehicle, the insurance company pays up you a certain amount which is equal to your loss, right? That is how it functions. Now for the company, there can be drivers who are good drivers, and there can be drivers who are bad drivers. Okay, there can be that sort of categorization. So some drivers might be bad and others might be good, right? And the premium for the good drivers should be lower as compared to the bad drivers, right? So lower premium should be charged ideally, and for the bad drivers the premium should be higher. Now the question is, how do you assess that, right? How do you assess whether a driver is good or bad? So for this, what happens in developed countries is that they have something called as telematics. What telematics means is that
they have these devices which are fit into your vehicle. Okay, these devices are fit into your car, and they track your driving style, they track whether you're over speeding or not, and they track whether you're getting any tickets or challans or not. And all of this data which is tracked by this device, it is sent back to the insurance company, and your premium changes real time. Okay, so if you are driving bad, your premium increases, and if your driving is good, your premium is reduced. And that is a perfect system. But what happens in countries like India is that telematics is not very common in this country. It's coming still. So in developing countries, telematics is not very it's not very popular. So insurance companies have come up with a way to incentivize the policy holders not to make a claim. Okay, so they basically, what they want to do is they want to charge the good drivers lesser premium, and they want to charge the bad drivers higher premium, right? And also they want to incentivize people not to make a claim, because under a motor insurance contract, if you see, there is no incentive to the policyholder to not make a claim, right? If I talk about the general insurance contract, if they don't make a claim, then the insurance company has a benefit that they won't have to pay up anything, and if they make a claim, the insurance company will have to pay them a benefit, right? But for the insurance companies, for the policyholders point of view, there is no benefit or loss if they have a claim or not. Okay, so they want to incentivize the policyholders not to make a claim. So how that is done is that, let's say there is a policyholder and you tell them that let's say to begin with, their premium is 1,000 rupees for a insurance contract of 1 lakh, a cover of 1 lakh, and the premium is 1,000 rupees. Okay, that is how they are starting off. Now the insurance company can tell them that if you do not make a claim in the first year, if there is no claim in the first year, your amount of premium would be reduced. You would get a 25% discount on your amount of premium. Okay, so from 1,000 it would be reduced to 750 if you do not make a claim, and if you make a claim, your amount of premium remains the same. Okay, this can be some sort of a scheme they can come up with. Okay, then in the second year, in the consecutive year, if you are on 750 rupees premium, if you again do not make a claim, you get a 40% discount on your initial premium. So 1,000 you get a 40% discount, so your premium becomes 600. Okay, if you do not make a claim. If you do not make a claim, so no claim, right? If you're not making a claim, you have a premium of 600. But if you make a claim, you again go back to 1,000. Similarly, if you are on 600, this is the maximum amount of discount that is possible. Let's say they won't give more discount than this. So if you do not make a claim, you still pay 600 in the next year. And if you make a claim, you go back to 750. Right. So that is the idea behind a no claim discount model, that you are incentivized not to make a claim. Now if I see this model, how is this a discrete state space and a discrete time set model? See, first of all, there are only 3 states in which a policyholder can be. They can either be paying a 1,000 rupees premium, they can be paying a 750 rupees premium, or 600 rupees premium. So there is a discrete state space. The state space for this becomes the premium level, that is 1,000, 750 or 600, right? That is your state space. And your time set, see, every time you transition, it is only possible at the end of a year. Okay, because in the first year, if you do not have a claim, that then at the end of the year you transition from the premium of 1,000 to the premium of 750, right? So the transitions are only possible at year ends. Okay, so the time set J is also discrete. It becomes the first transition can occur at time 1, and then the next transition can occur at time 2, and then 3, and so on. And you will have some initial premium, so that is at time 0, and so on and so forth. So at every year end, transitions take place, right? So this is a discrete state space and a discrete time set model, and these models, they are referred to as Markov chains. Okay, they are modeled by a, a particular type of statistical model that is called as Markov chain. We would be discussing more about Markov chains in chapter number 3. Okay, so that's my example for a discrete state space and a discrete time set model. Okay, next let's take the example of a discrete state space and a continuous time domain model. And this, if you have studied subject CT5, this would seem really familiar to you. So it was the healthy, sick, dead model, which you had studied in chapter number 10, competing risks of subject CT5. So healthy, sick, and dead. And if you are taking CT4 before CT5, I'll just explain it to you in a bit. So the healthy, sick, dead model tries to model the transition of a human life between multiple states. Okay, it models the transitions assuming that there are only 3 states: healthy, sick, and dead. That is, a person can either be healthy, he can be sick, or he can be dead. Okay, so what happens here is that a healthy person can become sick. Okay, and this arrow is indicating that. And then a sick person can again recover and become healthy. Okay, and sick and healthy people both can die directly from the healthy or the sick state. Okay, so this is our model. Now this is a discrete state space and a continuous time domain model. How? See, the state space is basically healthy, sick, and dead, right? So that's discrete. We have got a fixed set of values that the stochastic random variable can take, right? That the stochastic process can take. And as for the time domain here is basically between 0, okay, and infinity. Okay, so what this means is that these transitions between healthy, sick, and dead can take place at any point of time. Starting time 0, going up till at any point of time, going up till infinity, right? So what this means is that a healthy person will not become sick only at the end of the first year or only at the end of the second year. Okay, it will not happen only at discrete points. It can happen at any point of time, and a sick person can die at any point of time, and a healthy person can also die at any point of time. So the transitions are occurring in a continuous time domain. Okay, they can occur at any point of time. So this is my example for a discrete state space and a continuous time domain model. And these models, they are addressed in chapter number 5, which is called as Markov jump process. Okay, it's basically called as time homogeneous Markov jump process. Okay, and this is a Markov jump process, and we'll discuss this in detail. What does a Markov process and what does a Markov jump process mean? The word jump is used here because basically the transitions here are basically jumps from one state to another at any point of time. So they're like jumps from one state to another. That is why it's called as a jump process. We'll discuss the meaning of the Markov property very soon. Okay, so next is our example for continuous state space and discrete time domain model, and these models are a special type of models called as time series. And the best example for this is a stock market price. Okay, price of a stock. If you're observing the price of a stock at the end of every day, that is the closing price, it will take values at discrete points of time, and it would have a continuous state space because it can take any value in a continuum. So it can take, maybe if I'm talking about BSE Sensex, which is the stock market index for BSE, the Bombay Stock Exchange. It can take any value maybe between 0 and right now it's up to 35,000. So I can maybe say that it can take any value between 0 and 50,000, right? And it can take any of these values, right? And it's not only operating on discrete points, it can take any value in this continuum. Okay, so that's my state space for it. And the time domain, it would only be checked maybe at the end of every day or at the end of every month. So it'll take a check at time 0 and then 1 and 2 and 3 and so on and so forth. So this is a time series, and time series are these special kinds of models which have a continuous state space and a discrete time domain, and their theory, it is discussed in subject CT6. Okay, and CT6, there are two chapters which cover the entire theory relating to time series and how do you predict the price of a stock market index or a stock using the theory of time series. That is covered in subject CT6. Next is our continuous time domain and continuous state space process, and the best example for this is a general insurance process. What I can call this is as total claim in general insurance. Okay, so total claim in general insurance means that the total amount of claim that a general insurer receives in one particular year, it is a continuous time domain and a continuous state space process. How? See, the amount of claim, it is not fixed, it is not known in advance in general insurance. Okay, and it depends on the amount of loss. Okay, so it can take any value depending on the amount of loss. So the total claim I would receive in the year, it would depend on all the losses that my policyholders have suffered, and the time domain will also be continuous because such losses can occur at any point of time during the year. So the total claim for a general insurance company is a continuous state space and a continuous time domain process, and this is usually modeled, this is also covered in CT6, how do you model this process, and it is usually modeled using compound processes. And the best example for a compound process is a compound Poisson process, which we will be discussing in this chapter itself. Okay, so compound Poisson process is an example of a continuous state space and a continuous time domain process. Okay, so now that we have talked about time domain and state space, let's discuss a new type of process that are called as mixed type process. And what a mixed type process means, that its time set or state space, okay, either one of them is both discrete as well as continuous. Okay, so that is the property of a mixed type process. What this means is that a mixed type process, it is a combination of two different stochastic processes, and that is why it has two time sets or two state spaces. Let's see how this functions. Okay, let's take an example. Let's take an example of a mixed type process with a discrete as well as a continuous time set, right? So how does this work? Let's see. Okay, so what this means ideally is that if the time set of the process is discrete as well as continuous, the stochastic process will operate in continuous time but also change its values at predetermined discrete points, of time. Let's try to understand this taking an example. So what I'm considering as an example is something that they have given in the study material as well. It's the number of contributors for a pension scheme. Now contributors are all the people who are contributing premiums to the pension scheme still, right? That is, their salary is being deducted in order to provide for their pension or their retirement benefit, right? So how will this function? Let's say you have a population of a lot of people and they're all aged 60. Okay, and now you give them an option that you can start getting your pension and stop your contributions either it can happen through retirement. Okay, and you have given them an option that they can retire at the end of every year. They have an option of retiring at the end of every year. So they can either retire at 61, they can retire at 62, they can retire at 63, they can retire at 64, and they can retire at 65, right? And they can also exit the population of contributors by way of death. Okay, so retirement can occur at all these discrete points of time, but death can occur throughout this continuum, right? So death can occur at any point of time. So that is how this has a discrete as well as a continuous time set, because people, the number of contributors can reduce by way of death at any point of time. Okay, but they can reduce by retirement only at the end of each year. So the time set, if I see, I can divide this process into two processes. There can be a process of death and there can be a process of retirement, and that's what I told you. It's a combination of two different processes which are bundled up together. Okay, so you have got the process of death, okay, which would reduce the number of contributors. The number of contributors would have a discrete state space, of course. So they were initially 100 and they can be 99 and 98 and so on and so forth, right? The number of contributors will stay this way, right? And they can be reduced only at discrete points. But for the death process, the time set now, it becomes it is a continuous time set, right? So it can happen at any points of time in this continuum, or even after this, right? It can happen even after this. So it would be between 0 and infinity, right? So it can happen at any point of time. Death process can occur at any point of time. But the retirement process, again, it would reduce the number of contributors from 100 to 99 to 98, and the number of contributors can be discrete only, right? But if you talk about the time domain of this process, it can only operate at discrete times, that is at the age of 61, 62, 63, 64, or 65, right? So this gives me the time set of it, and that would be 1, 2, 3, 4, and 5. And you would have some initial number of contributors as well, so it would be defined at time 0 as well. So 0, 1, 2, 3, 4, 5 is when it can take values, when it can change the values of the number of contributors, right? So that is a good example of a mixed type process. Okay, now let's just take the example of a mixed type stochastic process which has a discrete as well as a continuous state space. Okay, and for this, again, I'm taking an example from the study material itself. So let's consider a car manufacturer. Okay, and this car manufacturer, what they do is they sell luxury cars. So what this means is that their cars are very costly and they are rarely sold. Okay, the number of sales would be low. Okay, so the source of revenue for this car manufacturer is two things. Okay, the first thing is sale of cars, which have a fixed price, fixed known price. Maybe the price of these cars is between let's say 60,000 and 65,000 for each car. Okay, maybe let's just take 5 discrete prices. Okay, let's take fixed prices. So it can be 60,000, 61,000, 62,000 up till 65,000. So they just have 6 cars here and their prices are these. Okay, and in pounds, of course. So the sales can be of these cars and they have got fixed prices, right? So sale of cars is one income and they have got a fixed known price, and the other source of income is regular servicing of the cars which have already been sold. So for sold cars, right? So they have two sources of revenue. One is sale of cars, and the other is through servicing these cars which have already been sold. Okay, so for servicing, the price is unknown, the price is not known. It would be a small amount and it would be an unknown price. Okay, so now if you're trying to model the bank balance of this manufacturer as a stochastic process, it is a mixed process. Okay, and the bank balance would change by the reason of two things: the sale of cars as well as the regular servicing, right? So for the sale of cars, let's consider the process of sale of cars. Now for sale of cars, the prices of these cars are already known, so the bank balance would change by a value which is pre-decided. Okay, so the state space here, it becomes, it is discrete, right? Because it would change by a known amount: 60,000, 61,000, 62,000, so on and so forth, right? And the time domain, so if I'm modeling the bank balance in one particular year, the time domain can be between 0 and 1, right? So time domain is continuous and the state space is discrete because I know the prices of all the cars, right? So this is one process, and the other process which is here is, the other process is servicing, right? And for servicing, the state space is continuous and the time domain is also continuous, right? So both of these things, they are continuous, right? So that's how it functions, right? So it has a state space which is discrete as well as continuous, but the time domain is continuous, right? So it's a mixed type process. Okay, so the next thing that I want to discuss with you is something called as a counting process. Now, a counting process, as the name suggests, is a stochastic process that counts. Now, what does it count? It counts the number of events that occur by a particular time. So if you are counting the number of events that have occurred by a particular time, you use a counting process. So how is it defined? A counting process is some process xt which operates in continuous or discrete time. So you can count in continuous or discrete time. So maybe you are counting continuously and you are observing maybe the number of cars that are arriving on a signal, or the number of buses that are arriving on a bus stop. Okay, so you can observe continuously, or you can observe every hour at discrete points of time, every hour or every week, that how a process is changing, okay, how the number of events are happening. And with this, the state space of this process is always the set of whole numbers, because when you count in whole numbers. So you have 0 events, and then 1 event, and then 2 event, and then 3 events, and so on and so forth, right? So that is the property of a counting process, that it may be a continuous or a discrete time process, but the state space is always the set of whole numbers, right? And xt is a non-decreasing function of time. Now what does this mean? Xt is a non-decreasing function of time, that the process, it only increases with time or remains the same. Because see, if in 2 hours 5 buses have arrived, in 3 hours 4 buses cannot arrive, the process cannot reduce. Okay, so if in 2 hours 5 buses have arrived, in 3 hours 5 or more buses would have arrived, right? The process cannot reduce. So if you're counting the number of events that are happening with time, the number of events would not reduce. That formally means that xt is greater than xs. The value of the process xt is greater than any other value xs for all the values of t that are greater than s. So if t is bigger than s, that is if t is a time span which is larger than a time span s, the number of events that would have happened in t in the time span t would be larger than the number of events that would have been that would have happened in the time span s. Then you can say that xt would be greater than or equal to xs, right? It can be greater than or equal to. So if no events would have occurred in the additional time, that is t minus s, then xt would be equal to xs, or it can be greater than xs, right? So it is a non-decreasing function of time. So that's what a counting process is. Okay, so the next thing that I want to discuss with you is the sample path of a stochastic process. So what do I mean by the sample path of a stochastic process? The sample path of a stochastic process is the joint realization of xt for all t's that belong to j. Okay, let's try to understand what this means. Let's take an example, okay? Now a stochastic process is a time dependent random variable, or it is a set of ordered random variable that change with time, right? So if I have one coin toss, if I toss a coin, it is a random variable, right? It's a static random variable. But if I toss a coin every minute or every hour, that becomes a stochastic process, because now every coin toss can be modeled as a random variable x1, x2, x3 that I'm tossing every hour, and each one of these is a random variable and they're dependent upon time now, okay? So they can take various values, okay? So now each random variable can take two values. Any xj can take two values. It can take value head, or it can take a value tail with a probability 0.5 and again with a probability 0.5, right? So this is an example of a stochastic random variable or a stochastic process, right? x1, x2, x3 going up till xt, where each xj is a toss of a coin, right? And which can take values head or tail. Now if I actually start tossing a coin, let's say I'm tossing a coin 5 times, right? That's my stochastic process, that I toss coins 5 times, one every hour. Okay, so if I toss a coin 5 times, I can get various outputs. I can get a head, head, tail, tail, tail. I can get a head, tail, head, tail, head. I can get all heads. And there can be multiple outcomes like these. There can be a lot of outcomes like these, different combinations of heads and tails, right? These all are called as sample paths. So when you run a stochastic process, and whatever outcome it leads to is called as its sample path. So once I tossed the coin and it led to 2 heads and 3 tails, that is one of my sample paths. If I toss it again, the outcome may be 1 head, tail, and then head and a tail and then a head, right? That is another realization, okay? That is why I called it joint realization of xt. So xt is a process, or in this case I can write it as xj is a process, right? Xj is a process which is time dependent, and I am checking the realization, whatever is the outcome of each output, okay? In this case, when I toss a coin 5 times, right? So these are various sample paths, okay? So a sample path is the joint realization of all the xt's for all t's that belong to j. So since I was checking it 5 times, here time set here becomes 1, 2, 3, 4 and 5. That is, I'm tossing coin 5 times, one every hour, right? And my state space, it becomes head and tail, right? And these are my sample paths, various paths that I could have taken, okay? And there can be many more of these, okay? So sample path is basically the realization of the process when you actually run it. Okay, so now that we are clear with the idea of what a stochastic process is and what is the meaning of a state space, a time domain, a mixed type process, a counting process, and what is the sample path of a stochastic process, let's discuss a few popular types of stochastic processes, okay? So these are a few examples of stochastic process that I am going to be discussing here. So the first example is something called as the white noise process, okay? Now it has a really fancy name, okay, but let's see what it means, okay? White noise process. So the word white noise, it comes from audio engineering. Actually, it is a word which is popular in audio engineering, where noise is basically the disturbance in any system, okay? and they have got various types of noises. There is white noise and there are other colored noises as well. So white noise process is a stochastic process that is used to model the white noise which exists in a system. Okay, so what it typically means for us in actual context or in statistical context is a white noise process is a set of independent and identically distributed ordered random variables. So if we have a stochastic process such as x0, x1, x2 going up till xn, okay, when we have such a stochastic process which is defined at time 0, 1 going up till n, and each one of these random variables is a IID, that is they are independent and they are identically distributed. That essentially means that they do not affect each other, their distribution does not affect each other, and it is exactly the same. So each xt follows the same distribution which is independent of all the other xt's. So an example of this can be, there can be an xt which follows normal mu comma sigma square distribution. Okay, so each xt here now follows a normal distribution with mean mu and variance sigma square. Okay, so this is a good example of a white noise process, okay, where each random variable is independent and identically distributed, and that is the definition of a white noise process. Okay, so for this your sample space may be discrete or continuous, and your time set j may also be discrete or continuous. The only important characteristic is that each one of these random variables is independent and identically distributed, and we have seen such an example when we were studying stochastic interest rate models in subject CT1, where each interest rate was taken to be a log normally distributed random variable, and each one of those was independent and identically distributed. That can be an example of a white noise process, right? So this is the definition of a white noise process. Okay, so this was one example of a white noise process. Another example can be xt. Now the only consideration is the distribution of all the random variables should be same. So this is another example with this distribution. Xt is equal to k, any constant k, with probability p. Okay, so the probability of xt taking a value is k is p, and a value of minus k with probability 1 minus p. This is another example of white noise process. One more example can be when k is equal to 1, this would be equal to 1 with the probability of p and minus 1 with the probability of 1 minus p. So these are various examples of white noise processes, and what these mean is that in this case xt can take various values. In this case the sample path can be like, the realization can be like, you can have values like k minus k and then k minus k, so on and so forth, right? So this is one of the sample paths that can exist for this kind of a process, and for this process you can have a sample path like 1 minus 1 1 1, any random ones and minus ones, right? So these are a few examples of a white noise process, and they the essential characteristic is that they are all independent and their distributions are identical, right? So that is what we must consider here. Time is equal to 0 and then 1 and then 2 and 3 and 4 and so on and so forth, right? Here also time is equal to 0 1 2 3. So these are the values that the process is taking. I can write xt is equal to these values, and here xt is taking all these values, right? So these are examples of a white noise process. Okay, so let's get to the next process now. Okay, so the second type of process we have is the general random walk. And what this means is this is just a sum of a white noise process. If you add a every value of the white noise process, it would give you a general random walk. So how do I represent this? Let's call it yt. Okay, the previous process I had called it xt. Let's give it a new name, yt. So yt is a process such that y0 is equal to 0. So it starts with 0. Okay, I'm just taking an example of a general random walk. It starts with 0, and each yt, okay, each yt is equal to the sum of, it is the sum of a white noise process. Okay, so let's call the white noise process xj now. So from j going from 1 to t, if I add a white noise process from 1 to t, okay, it would give me the general random walk at time t. So I have to write that xj is a white noise process. So if you add any white noise, process, it would give you a general random walk. Taking an easy example, let's say your white noise process was equal to, your xj is equal to k and minus k with probabilities p and 1 minus p, right? So if I evaluate my general random walk, what would it look like? Okay, I'm taking a sample path of the general random walk in this case. Okay, so what can be the values? Time can be like 0, 1, 2, 3, 4, 5, so on and so forth, right? So what can be the values that my yt can take now? At time 0, I've already told you that it is going to be 0. So it takes a value of 0, right? At time 1, what would it be? It would be the sum of the white noise processes till time 1, right? So let's say the first value that the white noise process takes is k. Okay, so if it takes k, my general random walk becomes k. Okay, I'm just adding 0 plus k is equal to k, right? Say supposedly next value that my white noise process takes is again k, so it becomes 2k, right? And then let's say the next value that my white noise process takes is again k, so it becomes 3k. Let's say the next value that the white noise process takes is minus k, so it becomes 2k again. And then next value can be k again, so 3k, and then 4k if it takes a value of k again. So that is how a general random walk moves. Okay, it's just like a walk. You're taking one step left or right, so you can have an increase or you can have a decrease, right? That's why it's called as the general random walk. So if I have to correspondingly plot my xt here, which was the white noise process, this is the general random walk. Okay, this is my general random walk process, and corresponding white noise process could have been like, I was at 0. If my xt took a value k, then it was added here, so it became k. Then again it took a value of k. Okay, and then at time 3 it took a value of k again. That is why it was increased from 2k to 3k. Then again probably my value was minus k, that is why it became from 3k to 2k again, and then a positive k, that is why it increased, then another positive k, that's why it increased. Okay, so basically what I'm doing is I'm just adding up all the white noise random variables, right? So I'm just adding them. So 0, I added a k, I got a k again. Then I added k again, which was this value, so I got a 2k. Then I added k again, I got a 3k. Then it took a value of minus k, so I got a 2k, which is 3k minus k. And then it increased with a k, so it became 2k plus k, that is 3k, and so on and so forth. So that's how a general random walk functions. It's just a sum of a white noise process, right? So you can just write it another way. Another way to write this general random walk is to write it this way: yt is equals to yt minus 1. Now yt is equal to yt minus 1 plus k with a probability p, and yt minus 1 minus k with a probability of 1 minus p. Now what this means is that whatever my value of the process was last at time t minus 1, okay, I just have to add k to it with a probability of p, and I have to add I have to deduct k from it with a probability of 1 minus p. So I can write it this way. That's what I've done here as well. So if I had 2k as yt minus 1, if this was my yt minus 1, so in order to get the next value, I would have added k with a probability of p, and 1 minus k, added minus k, that is deducted a k with a probability of 1 minus p. So since I got a k, I just added a k, and then it could have been minus k as well. Okay, so that's how it functions. So it's just a sum of white noise process, but I can also write it this way. Okay, so for this you can have a joint, and of course you'll have to mention that y0 when you start is equal to 0. So it's just starting from 0, and then you can have add a k with a probability p, and then you can deduct a k, then it can again become 0. If you have another minus k, then it becomes minus k. Then if you have another minus k, it becomes minus 2k. If you have an increase, it becomes minus k again. Another increase, it becomes k. So this can be your value of yt. I'm just adding k or minus k with probability p or 1 minus p. So this is another sample path. Okay, it can take various sample paths, right? So this is another sample path, but the conclusion is that I am just adding up my white noise process. So I just added all these values in order to get these values, right? And that is what a general random walk means. Okay, now there is a particular type of general random walk as well. So just to write my general random walk clearly, essentially general random walk is a sum of white noise process, which I can just write as I can write as yt is equals to whatever the previous value was plus k with a probability of p, and whatever the previous value was minus k with a probability of 1 minus p. Okay, that's the distribution of yt. Now if k is equal to 1, if k is equal to 1, then yt becomes yt minus 1 plus 1 with a probability of p, and yt minus 1 minus 1 with a probability of 1 minus p, right? This is referred to as a simple random walk, and the reason is that k becomes 1, so you're taking a simple random walk, which means that your steps have now become of 1. So this can be written, if I take a sample path. Okay, of course I have to start at 0, so y0 is equal to 0, and here also y0 is equal to 0. So if I start at 0, and then I can have an increase of 1, and then another increase of 1, and then another increase of 1, then a decrease, then an increase. So I'm just taking a walk. The way you can represent this is also this. You can just show it this way. You can this is something called as a transition diagram. If I draw the transition diagram of a general simple random walk, so okay, so we were at 0, and it can take values minus 1 and minus 2, and it can take increases 1 and 2. So it can increase with the probability of p, and it can reduce with the probability of 1 minus p. So if I'm at 0, I can go to 1 with a probability of p, and I can come to minus 1 with a probability of 1 minus p. Okay, similarly if I'm at minus 1, I can go to 0 with a probability of p and get to minus 2 with a probability of 1 minus p, right? Similarly if I'm at minus 2, I can go back with a probability of 1 minus p and go forward with a probability of p. So if the increases and decreases are only of 1, this is referred to as a simple random walk. Okay, and if they were of k, any arbitrary constant k, that's referred to as a general random walk, right? So you can go ahead with p and go back with 1 minus p. Okay, so this is what a simple random walk is. This is how you define a simple random walk if k is equal to 1, right? So this is your simple random walk. Okay, now there's one more thing which is called as symmetric simple random walk. So what does this mean? A symmetric simple random walk is just a simple random walk but where the probabilities of increase and decrease are equal. Okay, probabilities of increase and decrease are equal, which essentially means that p is equal to 0.5. Therefore 1 minus p will also be equal to 0.5, right? So the transition diagram looks somewhat like this. Let's just define it first. So now my process yt would be equal to yt minus 1 plus 1 with a probability of 0.5 and yt minus 1 with a probability of 0.5. So the probability of an increase and the probability of a decrease are just equal now, right? That is what it essentially means. Okay, so if I look at the transition diagram now, I have to start at 0. Of course, y0 is equal to 0. Okay, so I have to start at 0 and then minus 1 and minus 2 and 1 and 2 and 3 and so on and so forth. So the probability of an increase is now 0.5 and the probability of a decrease is also 0.5. Okay, so you reduce with 0.5 and you increase with 0.5 and then again you increase with 0.5 and then you increase with 0.5. So basically your probabilities have become 0.5, all of them. So basically p is equal to 0.5 in a simple random walk. The simple random walk becomes symmetric, right? And that's what's happened here. So that's my symmetric simple random walk. Now let's just take a few questions here so that you are clear on these things. Okay, so let's just take this question and try to see what's happening here. So it says for a simple random walk, calculate these three probabilities. So first of all, let's think about what a simple random walk is. So a simple random walk is defined as any xt, where xt is equals to xt minus 1 plus 1. Since it's simple, okay, simple means the increases and decreases are both equal and they're plus 1 and minus 1, right? So it's a simple random walk. And this increase happens with the probability of p and the decrease happens with the probability of 1 minus p, right? So that is what it means. Okay, let's see now how do we solve these questions. So the first part asks us that calculate the probability that x2, the value of the process at time 2 is equal to 102 and x5 is equal to 103 given that x0 was equal to 100. Okay, so let's just see what is happening here. Okay, so I'll have times 0, 1, 2, 3, 4 and 5. Okay, these are all the times that I have and they're telling me that I have been given that x0 is equal to 100. So x0 is equal to 100 and now I have to find the probability that x2 is equal to 102. Okay, let's write this as t and this is xt. Okay, x2 is equal to 102 and x5 is equal to 103. Okay, so how does it work? Let's see how do we solve it. Okay, so if x0 is equal to 100 and x2 is equal to 102, okay, so I want this process to increase 2 times. Okay, I want it to increase 2 times, right? That is only how it would go to 102, right? So this process can only increase by 1 and decrease by minus 1. That is what the process is, right? So it can only increase or decrease by 1. So if I want to, if I'm at time 0 I'm at 100, I'll have to take 2 steps and get to 102. That is increase 2 times, right? So the process will have to increase 2 times. So the probability for that would be the first increase, the probability would be p. The second increase, the probability would again be p. So this probability becomes p square, right? Now if I'm at 102, now if you see this probability, this means that we know that x0 is 100, okay, and we want x2 to be 102 and x5 to be 103 and we want both of these conditions to happen. So you can look at it like intersection. Okay, you can look at it like intersection or you can look at it like and. Okay, so it means that both of these things have to happen. So at time 2 we have already reached 102. Now at time 5 I want to be at 103. Okay, at time 5 I want to be at 103. So at time 2 I am at 102. So now how do I have 3 steps to take and I want to be at 103. Okay, so how will that happen? So for this to happen, see, if I want to be at 103 at time 5 and I'm at 2 at time 2 I'm at 102, I want 2 increases to happen and 1 decrease to happen. That is how it will happen, because an increase and a decrease will cancel out, and 1 increase would increase the process to 103. So since I have 3 steps and I want to increase by 1, 1 increase and 1 decrease have to cancel out, and then the process has to again increase in order to make it 103, right? So I want a increase, I want a decrease, so that these two cancel out. Okay, and then I want another increase. So when I increase it, it becomes 103. Then when I decrease it, it becomes again 102, and then when I again increase it, it becomes 103, right? So that is how how it will function. Okay, so for this to happen, I want 2 increases and 1 decrease. So p square 1 minus p. But then if you look at it carefully, this 2 increase and 1 decrease, it can happen in various ways. So how can it happen? You can have basically you can have multiple things happening here. Okay, so how will it function? Either you can have an increase first, a decrease, and then another increase, right? Or you can have a decrease first and then an increase and then another increase. Or what you can have is you can have 2 increases then a decrease, right? So all of these possibilities are there. So you can have increase, decrease, increase. You can have decrease, increase, increase. You can have decrease. You can have increase, increase, and decrease, right? So these all 3 outcomes will give you 103, right? So all the possible outcomes are to be taken into account. So this means that I want to calculate this probability. So if I want to calculate this probability, I want 2 increases first, that becomes p square, and then I want this to happen, or this to happen, or this to happen. In all the 3 cases, I'm adding them because either one of them can happen. So this happens, or this happens, or this happens. P square into 1 minus p plus 1 minus p into p square plus 1 minus p into p square. So if I add all of these together, so it becomes p square into 3 times p square into 1 minus p. So that becomes 3p to the power of 4 into 1 minus p. So that's my answer for it, and that is the probability that I need. Okay, let's look at the second part now. X2 is equal to 100 and x4 is equal to 103, given that x0 was equal to 100. Okay, so how do we do this? At time 0 I had 100. At time 2 I want 100 again. Okay, so okay, and then 3 and 4, and at time 4 I want 103. Okay, now let's look at this. How do I go about solving this? So from 100 to from 100 I want to get to 100 again between time 1 and 2, right? So first I can have an increase and then I can have a decrease, so I'll stay at 100, or I can have an increase or a decrease. Okay, they can reciprocate with each other, they can interchange with each other, right? So this becomes, there are basically 2 possibilities, increase and decrease, and decrease and increase. So this becomes 2 times p into 1 minus p, right? And then I want to get from 100 and I want to get from 100 to 103 from time 2 to time 4. Okay, so if I increase 2 times, okay, if I increase 2 times, I'll get to 101 and 102. Okay, so that is the highest possible value that I can attain. If I'm at time 2, I am at 100. To get to 103 at time 4 is impossible, right? Because even if I have to increase, I'll get to 102 by time 4, right? So it's impossible, right? So this is not possible. So you can this is an impossible event. So the probability is 0. So the entire probability becomes 0. This is impossible to attain, right? So this is impossible, right? And the last part, probability x2 is equal to 100 and x4 is equal to 102, given that x0 was equal to 100, right? So from time 0, I want to be at 100 itself at time 2, and then at time 4 I want to be at 102. Okay, so let's just see how does this work. So for time for the third one, what do I have? So I'm at time 0, 1, 2, 3 and 4, right? That's all I'm modeling. And I was at 100 at time 0, and at time 2 I was at 100 again. At time 100, at time 4 I was at 100 and I want to be at 102. So in order to calculate this, to get from time 0 to time 2 and staying at 100, I'll have to have an increase and a decrease. So the first is an increase, then there is a decrease, or there can be a decrease first and then an increase. So this becomes, there are two possibilities, adding both of them becomes 2p into 1 minus p, of course, okay, because they can interchange. And then I want to get from 100 to 102 in 2 steps again. So this has to be an increase and then another increase, right? So this is my probability. This becomes 2p cube into 1 minus p, and that is how you calculate this probability. So these are pretty easy to calculate, and that's how a simple random walk functions, and that's how you calculate its probability. When we'll study chapter number 3, we'll study simple random walks in more detail and discuss how to calculate more complex probabilities wherein you have a 50 or a 60 or 100 steps, right? Right now we are only looking at 3, 4, 5 steps and multiplying directly and getting the answer, right? So we'll discuss this in more detail. Let's move at the next process now. Okay, so the next thing that I want to discuss with you is the Poisson process. Okay, and Poisson process is something that you have already studied in subject CT3. This is just a stochastic version of a Poisson distribution. Okay, so let's see what this means. So Poisson process is a continuous time counting process. Okay, so it's a continuous time counting process, that is, we are operating in a continuous time and we are counting the number of events. This essentially means that the process, let's call the random variable for the process, let's call the process as nt. Okay, so the process nt, which is a time dependent random variable, it will not decrease with increase in time. So it would be a non-decreasing function of time because it's a counting process, and the state space for this process would be equal to 0, 1, 2, 3 because we are counting, right? And that's why the state space would be this. So a Poisson process is used to count events that are basically occurring at a constant rate of lambda t, right? That is the definition of a Poisson process, that if events are occurring at a constant rate of lambda per unit time, we are trying to count them. Okay, so if the rate in 1 unit of time is lambda, in t units of time it becomes lambda times t. Okay, and if you have t minus s units of time, it becomes lambda times t minus s. Okay, so whatever is the time unit, lambda changes with that, right? So that is what a Poisson process means, that when you apply this Poisson distribution, which is usually used in 1 unit of time, when you are seeing whether a particular event will occur, how many events will occur in 1 year, okay, when you apply it to more than 1 year, or when you apply it to t minus s units of time, that is when it becomes a Poisson process. So what I'm trying to see is how many events are occurring by a particular time. So for example, how many claims are coming for a general insurance company in 3 months or 2 months or 5 months or whatever the time period is, right? So that's what I'm trying to model. So this NT is the stochastic process that I'm looking at. Okay, so for this it has to have 3 properties. The first property is that N0 is equal to 0. That essentially means that at time 0 there would have been no events, of course, because we are counting events. So at time 0 there would have been no events. So N0 is equal to 0. NT has independent increments. That means that in non-overlapping time, so for example, in non-overlapping time, the number of events would not depend on each other. So for example, if you have had 5 buses which have come at a bus stop in the first hour, it would not influence the number of buses which would come in the next 1 hour. Okay, that would be independent of this, right? So no matter what the number of buses that would have arrived in the first hour, the number of buses that would arrive in the second hour will arrive at a rate of lambda, which is the rate of the Poisson process, right? So they will be arriving at a rate of lambda only, and the first hour's number of buses would not influence the number of buses that would arrive in the second hour. So for non-overlapping lapping times, the number of events are independent, and that is what we mean by independent increments. That is, the increases in the process are independent of the past of the process. Okay, let's write this. Increases of the process are independent of the past of the process. And that's what we mean by it, independent increments. Okay, we'll look at it in a bit of detail in a while. Okay, but for now it's that. And the third property is that the increments are Poisson distributed. Okay, so the probability that the number of increments in the time duration t minus s, that is nt minus ns, it is the increment over time t minus s, because the process at time t, it will have a value of nt, right? If nt is my stochastic process. Okay, stochastic processes I usually represent as xt, yt, nt, because they are time dependent ordered random variables, right? So nt is the value at time t, ns is the value at time s, right? So what would be the increment? Okay, since t is greater than s, I'm sorry, so let's write it the opposite way. So ns and nt, right? And at time s the value was ns, and at time t the value is nt. So nt minus ns is the increment, and the probability that this increment is equal to a constant n is equal to, now for your Poisson distribution with 1 unit of time, that is 1 year, the probability was of capital X is equal to small x was given by, that is, a random variable takes the value x. This probability was usually given by lambda to the power of x e to the power of minus lambda upon lambda factorial. Now here the rate has changed. The rate has become lambda times t minus s, because we are looking at a interval of time that is t minus s, right? Okay, so the rate has become lambda times t minus s, and the number of events that we want is n, right? So it becomes lambda times t minus s times n, so x is replaced by n, e to the power of minus lambda times t minus s upon n factorial. So it is exactly the same as your Poisson random variable, but it's just that the rate has become lambda times t minus s. Okay, so it's a stochastic version of a Poisson random variable, and that's what we mean by a Poisson process. And here n is equal to 0, 1, 2, 3, 4, because that is all the values that n can take. Okay, since we are counting the number of events that would occur in this duration, they can only be whole numbers, right? So that is why the state space, this is the state space, n can take values 0, 1, 2, 3, 4, so on and so forth. Okay, so that is what a Poisson process means, and if these three properties are satisfied, a process is referred to as a Poisson process. A stochastic process becomes a Poisson process, and we would discuss Poisson process in much more detail in the later chapter. This chapter is just an introductory chapter, just to get you acquainted with what are the terms, what are the things that we will be dealing with in the future. Right now we are just doing an introduction. Eventually we'll get into more details of these things, right? But you have to remember that it is a continuous time process, that is, we are checking over a time continuum. So j is equal to 0 to infinity, right? And your state space would be equal to 0, 1, 2, 3, 4. Okay, right? So I'm continuously checking, and the number of events that are occurring by a constant rate, and that is what a Poisson process is. Okay, let's just look at this. This is question number 3 from April 2010 exam. Okay, and it's pretty easy and straightforward. So the question is saying, for each of the following processes, state whether the state space is discrete, continuous, or can be either, and the time set is discrete, continuous, or can be either, right? And the processes are given as counting process, general random walk, compound Poisson process, and Markov jump chain. Okay, so let's look at this. Okay, let's just look at it. So for the first one, counting process. Now we have to assess the state space, that is S. What would it be? Discrete, continuous, or can be either. And time set, discrete, continuous, or either. So for a counting process, if I think about it, a counting process is a process that is in continuous or discrete time, but the state space is essentially the set of whole numbers, right? Because I'm counting the number of events that are happening one after the other. So the state space has to be discrete, yes, but the time set can be discrete or continuous. It can be either, because for a counting process it can be either. You can either count things that are happening continuously, you can count continuously, or you can count every hour or every minute or every year or whatever. Okay, so it can be continuous or discrete depending on when are you observing the process. Okay, next, general random walk. General random walk. So a general random walk is just a sum of a white noise process at every point of time. So how do I model general random walk? So general random walk is modeled as yt, where y0 is equal to 0. Of course, you're starting from something 0. Okay, or you could have started from 100 as well, as they had given in those examples, where yt is the sum of j going from 1 to t xj, and where xj is a white noise process. So I'm just adding a white noise process, adding a set of independent and identically distributed random variables at every point of time. So I'm just adding x1, x2, x3, so on and so forth. It's just a sum of these, right? That is what a general random walk is, and we have discussed this. So if I talk about the state space depends on the state space of these independent and identically distributed random variables. If the white noise process is something like normal, if xj follows normal mu comma sigma square distribution, okay, if that's the distribution, then it's continuous, right? Then xj is continuous, which would mean that the sum of this process, the general random walk, when I'll add up the values of such a process, okay, it can take any value for this process, mu comma sigma square. So since this is continuous, this would be continuous as well. And if my white noise process is discrete, that is, this takes values, maybe let's say it takes values k and minus k with probability p and 1 minus p, then my general random walk becomes discrete, right? So it can be continuous as well as discrete in terms of the state space, but time set will always be discrete because we are adding it at discrete points of time. That is why we use summation. We add up the independent and identically distributed random variables at each point of time, which makes it discrete. So that is why the general random walk is a discrete state space process, a discrete time set process, but the state space can be continuous or discrete, doesn't matter. Okay, next, compound Poisson process. What happens for compound Poisson process? So for a compound Poisson process, we just discussed it. First of all, talking about the state space and then the time set. Okay, so state space and time set. So for the time set, I know that a compound Poisson process has a continuous time set, because for a Poisson process, it is the definition that the time set is always continuous, right? That is what how we define a Poisson process, that it is a counting process which operates in continuous time. So we are observing events continuous time, right? So the time set is continuous, but the state space would depend on the nature of the IIDs that we are adding up. Okay, just like we discussed right now. So the state space would if it is the number of claims that we are adding up, or the number of claims for a storm that we are adding up, okay, up till time t, the state space would be discrete. And if we are adding up the total aggregate claim for a general insurance company, it would be continuous. So it can be both. Okay, and there can be other examples as well where the state space is discrete or continuous. Okay, so for a compound Poisson process, the state space is discrete or continuous, but the time set is essentially continuous. Now then the next question that they have asked is Poisson process. Okay, Poisson process. What happens for a Poisson process? The state space is a set of whole numbers. So it's discrete. Okay, it is discrete. And the time set is always continuous, because we are counting in continuous time. That was the definition of a Poisson process, right? So the state space is the set of whole numbers. It's 0, 1, 2, 3, so on and so forth. And the time set is continuous because we are observing in continuous time. We are counting in continuous time. And the last part that they've asked is for a Markov jump chain. Now we haven't discussed Markov chains. Okay, we haven't discussed Markov chains. Markov jump chain or a Markov chain is the same thing, right? And Markov chain, we discussed an example of it. We discussed the no claim discount model, and I told you that is a Markov chain. Okay, so thinking about a no claim discount model, if you think about it, there were only 3 slabs of premium there. You could have a 1000 rupees premium, you could have a 750 rupees premium, or 600 rupees premium, right? So that is what a no claim discount model is. And there the state space is discrete, and the time set, it can only change every year. Okay, you can only shift from 1000 rupees premium to 750 rupees premium at the end of a year, right? So the premium that you are paying, it changes only every year. So the state space is also discrete, the time set is also discrete, right? So that is how we can check for the state space and the time set of each of these processes. And these questions, they feature very regularly in the exam, so you should be thorough about assessing what is the time set or what is the state space. Let's look at another question now. Okay, so before we move on to the next question is a bit tricky, and it is an application of a compound Poisson process. I want to discuss with you the concept of probability of ruin. Now, probability of ruin is not covered in detail in subject CT4. It is a concept from subject CT6, but it essentially applies a compound Poisson process, and that is why I'm going to discuss it here. Okay, so think about a general insurance company. Okay, and for a general insurance company, we have already discussed that we can calculate the total amount of claim that they have received by time t as xt, where j is going from 1 to j is going from 1 to nt, right? That is the number of claims that have arisen, and I'm adding up all the individual claims. So let's call those individual claims as yj. So if I add up all the individual claims that are independent and identically distributed over all the number of claims, I would get the total claim amount. Okay, so this is my equation for the total claim amount, right? And this is a compound Poisson process, right? And we have already discussed this. Now the probability of ruin basically as a word means that a company is ruined when they run out of money. Okay, and that is what it means in context of general insurance company as well. That is, they're ruined when they do not have money to pay off, they become insolvent, essentially meaning that. Okay, so if just let's think about one policy, let's think about that a general insurance company has only one policy. Okay, and we want to calculate its probability of ruin. Okay, so if they begin with the initial capital of let's say u, let's call the initial capital as u. Okay, so insurance company started, they had a capital of u, and they're selling only one policy. Okay, and let's just say they receive premium at a rate of ct. Okay, where C is the rate of premium and T is the unit of time. So premium is received as C per unit time. Okay. So what would be their probability of ruin? Okay. So probability of ruin is denoted as psi of u. Okay. Psi is a Greek letter. U is the initial surplus. So for an initial given initial surplus, the probability of ruin would be the probability that you started off with a capital of U and then you added off some premium to it. Okay, you are continuously receiving premium. So you by the time t, okay, the probability of being ruined by time t, by any random time t, is written as psi u with a subscript of t. Okay, so what is the probability that a company is ruined by time t? It would be equal to psi of u plus ct. Ct would be the premium that you would have received by that time minus the amount of claim that you would have paid by that time. So that would be equal to xt, right? Because that is the total claim for a general insurance company by time t, right? And if I want this company to be ruined, this thing should be less than 0. This is the amount of money that they're left with. Okay, so if this thing goes below 0, this means that they're ruined. Okay, so if they started off with a surplus of u, and then they received by time t, they have received a premium of ct and paid claims xt, which are much more than these two things, that is when they'll be ruined. So this figure would come out to be negative. Okay, and that would mean the company is ruined, right? And this is the concept of probability of ruin. Okay, now let's do a question in order to apply this and see how this is examined in the exam. And this was examined once back in 2007. So I'm just gonna do that question with you right now. So let's look at this very interesting tricky question. A particular baker's shop in a small town sells only one product, currant buns. Okay, so there is a baker who is just selling one product, that is currant buns, and these currant buns are delicious and customer travel many miles to buy them. Okay, unfortunately the buns do not keep fresh and cannot be stored overnight. So he bakes every morning and then he has to finish his stock by the end of the day. The baker's practice is to bake a certain number of buns k before the shop opens each morning, and then during the day baking c buns per hour. Okay, so he has started off, you can think about this like an insurance company who has started off with a capital of u. Here the baker has started with a initial number of buns of, okay, k, right? So the initial number of buns that the baker has are equal to k, right? And then he'll continue baking buns every hour. So the amount of buns per hour is c. So the amount of buns for every t hours would be ct, just like the premium we used to receive. So additional buns, right? So this is a very similar kind of a model, right? Just like probability of ruin model, right? He is concerned that he does not run out of buns during the day. So he does not want to be ruined. That is, he does not want to run out of the buns. The number of buns left over at the end of each day is as few as possible. He wants the minimum number of buns to be left so that they are not wasted. Describe a model which would allow you to estimate the probability that the baker will run out of buns. Okay, so now and state the assumptions you make. Now see, the thing is that we already know the amount of buns he begins with and the additional buns he makes. All we need is the number of buns that he'll sell by time t, right? So that we can estimate the probability he does not run out of buns, right? So I'll have to figure out a time t by which he may run out of buns, and that is the probability that I want to model, right? So let's just use the symbol which they have given us in the question itself. In the second part, they have written determine the relevant expression for the probability that the baker will run out of buns in terms of k, c and bj, the number of buns bought by the jth customer. So let's call bj the number of buns bought by the jth customer. Okay. And let's now so now this is our you can think about this as the claim amount. Okay, the number of the amount of claim from the amount from the jth claim, right? That is how you can think about it. So this is the number of buns bought by the jth customer. Right, so you have the initial buns, you have the additional buns, and the number of buns which are bought by the jth customer. And we need to model the number of customers that arrive per unit time as a Poisson process, right? Because so as to make it compound Poisson, right? So nt is the number of buns, okay, no, number of customers that arrive by time t. So as a compound Poisson process, what I can model is the number of buns which are sold by time t, right? That I can call as xt probably. So xt can be modeled as j going from 1 to t, right? 1 to nt, in fact. For every customer I'm adding, okay? So for up till time t, I'll add for nt customers, because that is the number of customers that have arrived by time t, and this follows a Poisson lambda t process, right? Let's say it follows a Poisson process. Nt is following a Poisson process. Okay. So I have to add up all the total buns. Okay, that would give me bj. So bj is added up till time t. This is the total buns sold by time t. So now they are asking us determine the relevant expression for the probability that the baker will run out of buns. Okay, and I want to just give an expression for the probability that the baker will run out of buns. The first and the second part are almost the same. In the second part, they've just given you to asked you to introduce it, bj, and express it in terms of that, right? So I want to express the probability that the baker will run out of buns. So when will it run out of buns? When will he run out of buns? It would be the probability that I started off with k buns initially, okay, and I'm trying to model the time t by which the baker will be ruined or he'll run out of buns. So k plus ct is the total buns that I have made by that time, and out of that I have sold xt buns, right? I've sold xt buns, and if this figure it is less than 0, okay, that means I've run out of buns, right? So if this is less than 0, that is if I've sold more than I've made, then I'm ruined, then I'm out of buns. So this is less than 0. This is the probability that I need. And in the second part I want to express it in terms of bj, right? So how can I express it? I can write it as b probability that k plus ct minus this xt can be written as j going from 1 to nt, and bj, right, is less than 0. So this becomes probability that k plus ct is less than j going from 1 to nt bj. Okay, so I'll run out of buns when I've sold more than I've made by that time, right? And this would be the probability, where you'll have to define what nt is, because they haven't written nt in the question. So you'll have to define nt as the number of customers that arrive by time t. Okay, and it's following a Poisson lambda t distribution. That is, it's a Poisson process with a constant rate lambda, right? And that's your answer for this question. That's all you need to do in this. Okay, so 4-mark question, this is what you needed to do. And this is probably the only tricky question in the past let's say 20 diets. In the past 20 diets, this has probably been the only tricky question that has featured. Okay, and it was only for 4 marks out of these 2 chapters, the first chapter and the second chapter. Okay, so we have solved it, so you won't have a problem with it. Now let's just move on to the next topic. So the next question that we are trying to address is that how do we define a stochastic process completely? So say supposedly we have a stochastic process xt such that t belongs to a set which is 0, 1, 2, 3, 4, so on and so forth. So we have these set of random variables, ordered random variables x0, x1, x2, x3, so on and so forth, right? If we want to define this stochastic process completely, okay, how do we do that? So for that we need two things. The first thing is that in order to define the this stochastic process completely, we need the distribution of each of these random variables. So the first thing is that we need is the marginal distribution, right? Marginal means individual distribution of these random variables. Okay, marginal distribution x0, x1, x2, so on and so forth. So if we are able to define these random variables completely, we'll be able to define the stochastic process completely. The second consideration is that if there is a relationship between these random variables, that is if they are dependent upon each other, then we also need the covariance of these terms. So we need the covariance of x0, x1, x2, so on and so forth. So we need to define the dependence as well as their individual distribution. So when I take both of these together, the marginal distribution as well as the covariances together, they are referred to as the joint distribution. Okay, the joint distribution of x0, x1, x2, x3, so on and so forth. So for any random variables which are dependent upon each other, which have a covariance, in order to define the stochastic process completely, we need to define their joint distribution, which essentially means their marginal distribution as well as their covariances. Okay, and in the marginal distribution, when I talk about it, I need to define the mean, okay, and the variance of these random variables, individual means and variance. And when I talk about the mean, this gives me an idea about the size of the random variables, that is what is their central tendency, what is their one value which can represent the model the random variable completely, and variance talks about the spread of the random variable. Okay, and along with that, if they are related with each other, I also need to define the covariance. So if you define these three things, you have defined the joint distribution of these variables, and which would help you define the stochastic process completely. Okay, and now if these random variables, they are independent of each other, they are not dependent upon each other, then this covariance term becomes 0, okay, when independent. Then you only need to define the marginal distribution in order to define the joint distribution completely, because if they are independent, the covariance would be 0. Okay, so the next thing we are about to discuss are some important properties of stochastic processes. And these properties, if you have studied subject CT6, you would have already come across. So you would know about these properties if you have studied subject CT6. The first property is called as stationarity. Okay, and what stationarity means is that the joint distribution or the statistical properties of a stochastic process do not change with time. Okay, so what that essentially means is that the distribution of the stochastic process would remain same even when time elapses. Okay, so the distribution does not change. The statistical properties, that is the mean, the variance, they do not change over time for a process. So essentially for a stationary process, your expectation of x0 would be equal to the expected value of xk. Okay, so basically what this means is the value that you will expect for x0 would be same as the value you will expect for xk. Let's assume that the stochastic process that we are talking about is roll of a die. Okay, if you are rolling a die, okay, if you are rolling a die k times, In the first roll, your expectation, your mean would be 3.5. Okay, that is how you calculate the mean for a die. You just multiply each value by its probability, so you get 3.5. It's a discrete uniform distribution, right? So your expectation for the first roll would be 3.5, and your expectation for the kth roll or any other roll would be 3.5. So your expectation is constant, and that is what I mean when I say statistical properties remain unchanged as time elapses. We'll check for other statistical properties as well. And to get more particular, there are two types of stationarities that exist: strict stationarity and weak stationarity. Okay, so what do I mean by strict stationarity? Okay, a strict stationarity is a more stringent condition for stationarity. Okay, that is, it is very hard to satisfy, and any stochastic process rarely satisfies it. It says that the joint distribution of xt1, xt2, xt3 going up till xtn, the joint distribution of these random variables, that is their marginal distribution as well as their covariances, they're same as the joint distribution of xt1 plus k, xt2 plus k, xt3 plus k going up till xtn plus k. So what this means is that the joint distribution remains same as time has elapsed. Okay, so even after k years, the joint distribution is exactly the same. Okay, and this is the definition of strict stationarity. This condition is very hard to check, and this is much more hard to fulfill. So this is not a very practical sort of a approach. Okay, so therefore we have a practical sort of approach that is a more lenient condition, and that is called as weak stationarity. Okay, so you must understand one thing, that every process which is strictly stationary is also weakly stationary, but the corollary is not true. Okay, so every process which is weakly stationary is not essentially strictly stationary. So this is a more lenient condition. Okay, so what does this say? This asks for only two things. The first thing is that expectation of xt should be constant. Okay, so the expectation of each random variable in a stochastic process should be exactly the same. Okay, expectation at every point of time should exactly be the same. And the second condition is that the covariance of xt and xt plus k, okay, that is the covariance with a time lag of k years. The covariance with a time lag of k years depends only on the time lag k. That essentially means that if you calculate the covariance, which is calculated as expectation of xt into xt plus k minus expectation of xt into expectation of xt plus k. We know this definition from subject CT3 for covariance. So if you will calculate this covariance, this would turn out to be a function of k. You won't find any t in it. It would just be a function of k, and it won't depend on the initial time but just on the time lag. So it depends only on the time lag, and it is essentially a function of the time lag. Okay, and this is something you need to know when you are trying to check for weak stationarity. Okay, so you need to check for the expectation first and then for the covariance, whether it is just turning out to be a function of k or not. Okay, so let's move on to the next property now. Okay, so the next thing we are trying to study is something very important, and it forms our base for almost next 3 to 4 chapters and the entire subject. Okay, so I want you to be really patient and thorough with this. So we are trying to study the Markov property. Okay, what does the Markov property means? So essentially what Markov property means is that the future states of a process can be completely deduced or sufficiently predicted given the information of the present state. Okay, if we know the present, we can sufficiently predict the future without any additional information from the past. Okay, so if we know the present state, we can sufficiently predict the future, and the past does not provide any additional information for the prediction of the future than the present. Okay, so if you know the present, you can predict the future even if you don't know the past. right? So past is not giving us any additional information, and that is what the Markov property says. So let's write it formally. So the Markov property means that the future state of a process can be sufficiently predicted by the present state and the past states do not provide any additional information for the prediction what this essentially means that is that the all the information from the past is contained in the present state. That is, if you know the present state, you do not need the past states because all of their information, all of their relevant information is contained in the present state. Okay, how do we write this mathematically? Let's see, how do we represent this mathematically? So mathematically, the Markov property is represented in a bit of a different fashion for discrete state space processes and the continuous state space processes, and we'll try to understand the logic behind that. Let's just first see the discrete state space version. So it just says that probability that xt is equal to a. So there is a process that is going like x 0. Okay, let's just see how this process is going. Let's say it's going from time, it starts at time s1, so it's going like x s1, x s2, x s3, and then it's going up till xs, and then further it's going up till xt. Okay, that's how the process is functioning. I'm calling all of these past states as past. Okay, this is the current state that I know, this is the latest states that I know, latest state that I know. So this is the latest known, or you can call it the present. Okay, and this is the future. So what I'm saying is that I do not need to know about these things. This latest known state is sufficient to model the future state. Okay, so this means that the probability of the future state, that is xt being equal to a, given all the past states, that is xs was equal to x1, xs2 was equal to x2. Okay, all these states, given all these states and the present state xs is equal to x, is same as the probability of the future state being a, xt being a, given the present state. So this past, it can just be eliminated. It does not provide any essential information. So I'm just saying this probability is same as this probability. This is equal to this, which means that this past is irrelevant, so we can just remove it. Okay, so that's just saying that xt is equal to a, given that xs1 is equal to x1, xs2 is equal to x2, going up till xs is equal to x is same as probability that xt will be a, probability that is this will be a given the present state, that is xs is equal to x. And then for all these times they are just indicating that s1 is less than s2, which is less than s3, and all of these are less than t, right? So that is how things are going, and all these times they belong to the time domain, that is j, or the time set, right? And all these values x1, x2, x3, x and a, all of these they belong to s, they belong to our state space, that is s. Okay, so that's what this definition is saying. So for all of these states, the future can be completely modeled by the present and the past is irrelevant. Okay, that's how we interpret this. Now this was the discrete state space version, that is when the state space was discrete, we can write it like this. Okay, but in continuous state space, we have already studied it from subject CT3, that for continuous random variables, you cannot write probabilities at a particular point. Okay, you cannot define probabilities like xt is equal to a, because for any continuous random variable, suppose a continuous random variable is defined over range of 0 to 1 maybe, right, and you want the probability that x will be equal to 0.5. okay, x belongs to this range and you want x to be equal to 0.5. now probability is total outcomes upon favorable outcomes upon total outcome, so your total outcomes are infinite, right? Between 0 and 1 there can be infinite values. Since this is a continuous random variable, it can take any of these values, right? So there are infinite values and you want this particular value, that is 0.5. okay, so that is just one value you want out of all these total values, so 1 upon infinite would be 0. So if you will check the probability at a particular point, it would turn out to be 0. So we need to check the probability in a range, right? That is how we used to check it in subject CT3, probability that x would be between 0.4 and 0.6. We can calculate something like this. This would give us a result. We used to do it using integration, right? So for continuous random variables, probabilities cannot be defined at a point. They are defined in an interval, right? Similarly, we'll change the Markov property and we'll define this xt is equal to a. Instead of this, we'll make xt in an interval. So how do I do that? We'll just say xt belongs to a. So probability that xt belongs to a given all the past. Now these values are equal to, because they are known values, they are past values. Okay, these are not, we are not talking about probability here. These are all past values which are known. They are saying that xs1 turned out to be equal to x1, xs2 was x2. okay, in the past we know this. This value also we know, xs is equal to x, it is known, right? At time s all these values are known, okay, but xt is not known, right? So we'll just, when we talk about the probability, we'll write xt belongs to a, where a is a range of values. Okay, so we can talk about probability in terms of a range. Okay, again this value is equal to probability that xt belongs to a given that xs is equal to x, right? So the past is irrelevant and only the present matters. So we have just written it as future state given the present state, and the past is irrelevant. And this is for all the x, s1, s2, s3 going up till xt which belong to j. Okay, and a is a subset of s here. A is a subset of s. That means that this a, it contains some values. Okay, it contains some values out of all the values which are in s. Okay, of course we know that all the possible values that a stochastic process can take, all possible values are contained in the state space. So a has to be a subset of s, right? So for that we are checking the probability and we are checking it in a range or in a set, right? That's how we do it. Okay, so that is the Markov property for you, and this is what the Markov property means. Let's continue our discussion a bit further on Markov property. Next thing I want to talk to you guys about are increments and what does independence of increments means. Okay, so this is the third property that we are discussing. We have discussed stationarity and Markov already. Let's talk about increments and their independence. Okay, so if I talk about the increments, okay, what are the increments of a process? Increments are changes in a process basically over a period of time. So let's say maybe this is the timeline and these are my states. Okay, right? So let's say at my timeline, let's write this as the stochastic process. Okay, this is my time and this is my stochastic process which is taking values. So let's say at time t, okay, at time t my process has a value of xt, right? And at time t plus u my process would have a value xt plus u, right? So what would be the increment over time u? This is the time duration u. The increment in the process would be equal to the change in the process value over this time. So it would be xt plus u minus xt. Okay, and this is the increment of the process over the time duration u, right? And when will we say that this process has independent increments? When this increment xt plus u minus xt, this is independent of all the past of the process up till xt. Okay, so up till this time xt, all the past of the process does not affect this increment. And we have read this in the Poisson process, that the Poisson process has independent increments. This means that if I'm observing the arrival of cars which are arriving at a Poisson rate, as a Poisson process over 3 hours, the number of cars that have arrived in the first 2 hours don't affect the number of additional cars that will arrive in the last 1 hour, right? And that is what independence of increments means. So this just says that xt has independent increments if xt plus u minus xt, that is the increment over the time duration u, is independent of all the past, of the process xs. The past is referred to as xs, where s is less than equal to t. So whatever the values that this process had taken till here, that were xs, and this is up till time t. Okay, so even xt does not affect the increment, right? That is why it's less than equal to. So all the values up till this point of time that this process has taken, okay, all the values are written as xs, all these values, okay, up till t, do not affect this increment. Okay, and a special thing about independence of increments is that any process which has independent increments also has the Markov property. Okay, so independence of increments, because if your future increment is independent of all the past, your future value will, which is just your present value plus the increment, will also be independent of the past and just dependent upon the present value, right? So independence of increments implies the Markov property, right? But again, the corollary is not true. Markov property does not imply independence of increments. Okay, so although all the processes that have independence of increments have the Markov property, but all the processes that have the Markov property do not have independent increments. And why is that? We'll see the reasons in a while. But the first thing I want to discuss with you guys is how to check for Markov property, because checking for Markov property is very important, because our next 4 to 5 chapters will depend upon Markov property entirely. Okay, it depends on that being true, that future can be completely modeled by the present state and it is independent of the past. So how do I check for the Markov property? Okay, how do I check for the Markov property? First thing that we know for certain is that if a process has independent increments, it will have the Markov property. So first thing I need to check is independence of increments. If it has the Markov, if the process that I'm checking for a process xt, if it has the independence of increments, if it is there, yes, then it implies that the process is also Markov, right? Then it is a Markov process. Any stochastic process with the Markov property is referred to as a Markov process. Okay, and we'll deal with the types of Markov processes very soon. We'll see what the different types of Markov processes that are covered in our curriculum are. Okay, so if there is independence of increments, it implies the Markov property, right? But if we do not have independence of increments, so if there is a no here, right, then the process still may be Markov. We'll have to check for the definition of the Markov property. Okay, if it satisfies the definition of the Markov property, we'll see an example of this. How do we do it? question. If it satisfies the definition of the Markov property, then if yes, then it implies Markov. It's a Markov process. If it doesn't satisfy this definition, then it's not Markov. So the first thing that you need to check is for independence of increments, and if that is true, then it's a Markov process. If it is not, you have to check if it still satisfies the definition of the Markov property. If it does, it's a Markov process. If it doesn't, then it's not a Markov process. Okay, so that's how we check for it, and let's take an example in order to check for the independence of increments and the Markov property. Okay, so let's take two questions. The first one is prove that the random walk has Markov property. So how will we prove that? We'll try to first check for independence of increments, and then we'll check for the definition of the Markov property. Now how do I define a general random walk? When they say random walk, they mean general random walk. Okay, so question number one, let's try to do it. So a general random walk is any process xt where xt minus 1 plus k, okay, it increases with the probability of p, and xt minus 1 minus k with the probability of 1 minus p. Now since we can see that these increments of this process are just xt minus xt minus 1, so I can just change this. I can just reduce xt minus 1 from xt, right, and this would give me k with the probability of p, and minus k with the probability of 1 minus p. So we can see that the increases in this process, or the increments, they are just a white noise process. And that's how we used to define a general random walk, that it is a sum of white noise processes, right? When we add up white noise processes, it makes a general random walk, right? So as the increments are independent, okay, they are independent because white noise processes are IIDs. They are independent and identically distributed random variables, and you can see that this increment, this value that of increment, that it will be k or minus k with the probability of p or 1 minus p. So this value does not depend on what the value of x or t minus 1 was or any other value before that. It's just independent of those, right? So it does not depend on the past of the process, and thus it has independent increments, and thus it has the Markov property. You'll have to write here that the increments of a random walk are IIDs, independent and identically distributed random variables. Therefore, it has the Markov property. We can clearly see that probability of this increment taking a value k or minus k, it does not depend on the past values. It is independent. It is just p and 1 minus p. So it has independent increments, yes. Okay, and therefore it has the Markov property. Let's see the second one. Okay, the second question says consider a discrete time process. Okay, there's a discrete time process on the integer defined values as xt. Now they have defined values for xt as xt minus 1 plus it. Okay, it can take incremental values xt minus 1 plus it, where it is a random variable. It is a random variable which can take value plus 1 or minus 1 with probability e to the power of minus xt minus 1, and the probability of taking a value minus 1 is qt, that is 1 minus e to the power of minus xt minus 1. Is this process Markov? Does it have independent increments? Let's see this one. So it's just this. So if I rewrite it, I can write it as x t minus 1 plus 1 with a probability of pt, that is e to the power of minus mod of x t minus 1, right? And it would be x t minus 1 minus 1, because it can take another value which is minus 1, with a probability of 1 minus this 1 minus e to the power of minus x t minus 1, right? So what are the increments of this process? If I try to see the increments of this process, I can write them as it, right? So it are the increments, and it can take value plus 1 or minus 1, with a probability of 1 e to the power minus x t minus 1 and 1 minus e to the power of minus x t minus 1, right? That's how I can write it, right? So if I look at this process now, the increments are now dependent upon the past values of this process xt. See, it will take plus 1 with the probability e to the power of minus xt minus 1, which is a past value of this process. So this increment, it is not independent of the past values of the process, right? We can see that it is not independent. It depends on the last value. So basically what we'll find out is that it can take a value of plus 1 or minus 1 depending upon what the last value was, right? And the probability changes, okay? So it does not have independent increments. But does it still have the Markov property? Let's see that. See, xt is equals to xt minus 1 plus 1 with a probability of e to the power of minus modulus xt minus 1, and xt minus 1 minus 1 with a probability of 1 minus e to the power of modulus of minus modulus of xt minus 1. Now here if you see this value, the next value of xt, it just depends upon xt minus 1, okay? It just depends on the previous value, okay, and not the values before that. So if the current value is xt minus 1, I can use it to predict the probability of the next value xt, because it just depends on the current value. It does not depend on t minus 2, it does not depend on t minus 3, it just depends on the current value, that is t minus 1, right? xt minus 1, and that this can be used to completely model the value of xt, right? So the past values will not give you an additional information, and thus this has the Markov property. This is Markov because it just depends on the current value, it just depends on the latest value. So if you see xt minus 2, xt minus 1, xt, okay, so xt just depends on the last value xt minus 1, right, and not the values before that. So it has the Markov property. Present can be used to model the future completely without the knowledge from the past, right? So the past does not influence the future, just the present does. But it does not have independent increments because the increment also depends on the present value, which it should not. That was the definition of independence of increments. So here the process is Markov, but it does not have independence of increments, okay? So there can be processes which are Markov but do not have independence of increments, and this is dependent on the current value, okay? That's why it's Markov, because it just depends on the current value, but it does not have independent increments because the increment depends on the present value, which it should not, okay? That's how we defined it. That's how we defined independence of increments, that xt plus u minus xt is independent of xs, where s is less than equal to t. So this xs covers xt as well, right? So it should be independent of xt as well. But then here it is not independent of xt minus 1. It is not, okay? It's not independent of the current value. The future value that it will take at time t, it's not independent of xt minus 1. Thus it does not have independence of increments, but it does have the Markov property because it just depends on the present value. So I hope you understand that now. Okay, so let's just discuss whether the Markov property and the stationarity property applies to the four processes that we have discussed or not. Okay, to begin with white noise, see, white noise is a stationary process because it is in fact a strictly stationary process because its statistical properties do not change over time because it is a set of independent and identically distributed random variables. So since all of the random variables have the same distribution, the joint distribution also remains the same, and since they are independent, their joint distribution is same as their marginal distribution, right? So they do not have any correlation amongst them, and their distribution remains the same because they are identically distributed, thus they have the stationarity property. They also have the Markov property because they do not depend on each other. Okay, so I do not need the information from the past in order to predict the future, right? Okay, so I even do not need the information from the present because future would be independent of the present as well, right? Because they are a set of independent and identically distributed random variables. So xt doesn't depend on xt minus 1 as well. It does not depend on this. Why? Because they are all independent and identically distributed. Independence means that they do not depend on each other. Okay, so it has the Markov property as well, right? So that is something we can conclude. About the random walk, see, random walk, the increments of the random walk are independent and identically distributed random variable, that is white noise. Okay, its increments are white noise, therefore it has independent increments, thus it has the Markov property. About stationarity, a random walk is not stationary, and the reason for that is that as time elapses, the value of the random walk will keep on increasing. For example, you would expect a higher value from a random walk. Okay, so for example, expectation of x 100, the value after 100 steps, let's consider a random walk, xt is equal to xt minus 1 plus 1 with a probability of maybe let's say 0.9. It increases with the probability of 0.9 and reduces with the probability of 0.1. So the probability of 100 x 100 would be much higher as compared to the probability the expectation of x 100 would be much higher as compared to the expectation of x 0. Expectation of x 0 would be 0 certainly because we are starting from 0. Okay, but then till 100 there would have been a lot of additions, and since there is a higher probability of addition, this would be a very much greater value. So expectation is not constant, that means it is not even weakly stationary, so it cannot be stationary, right? Now talking about the Poisson process, it has the Markov property because it was in the definition of the Poisson process that it has independent increments, right? It is a process with independent increments, so it has the Markov property. About the compound Poisson process, its increments are IIDs, we know that, because compound Poisson process is a sum of IIDs. Okay, it is a sum of independent and identically distributed random variables. That is how it is defined, right? So it has the Markov property again because both of these have independent increments, and thus they have the Markov property because in this the definition itself says it, and this is a sum of independent and identically distributed random variables. That is why it has the Markov property. Now talking about stationarity, Poisson process won't be stationary because you would not expect the same number of cars to come in 10 hours as you would expect to come in 1 hour. Okay, so the expectation would increase with time. You would expect more cars to come as time increases, right? So the expectation of x10 is not same as expectation of x2, right? So you would expect more cars, and thus it is not stationary. Okay, and last, compound Poisson process. Now again you would expect a higher claim in 1 year as compared to the claim in 1 month, right? So the expectation would increase with time again, so it does not have stationarity. For weak stationarity, the first consideration is that expectation should be constant, and in 3 of these expectation is not constant. But since white noise has stationary properties, its expectation remains the same, its statistical distribution remains the same, everything remains the same. Okay, so that's for all the processes that we have discussed here. Now let's talk a bit about Markov processes, right, and then end this chapter. So if I talk about Markov processes, the Markov processes which have a discrete state space and discrete time set. Okay, discrete state space and discrete time set, right? Let's write as discrete S and discrete J, right? These are called as Markov chains. These processes are referred to as Markov chains. Okay, and they are covered in chapter number 3. And I had discussed the no claim discount model with you. We will assume that the process has the Markov property that the past premium that the policy holder has paid will not influence his future premiums, right? His future discounts that he will get. So we'll assume the Markov property, and we already know that it has discrete state space and a discrete time set, and therefore it would be modeled as a Markov chain. Okay, in chapter number 3, and that is what chapter number 3 is about. Okay, the Markov processes which have a discrete state space but a continuous time set, okay, discrete state space but a continuous time set, are called as Markov jump processes. Now one example of this can be the healthy sick dead model which we had discussed. Okay, and there are various kinds of Markov jump processes, and we will discuss these over the due course of time. These are covered in chapter number 4, 5 and 6, and that is our content for the next few chapters. Okay, so we'll be talking a lot about Markov processes. You should be clear about what the Markov property means and how do you interpret it. Okay, and how can it be applied. Okay, so let's see that in the next chapter. This was all for this chapter. A few small topics are left, which I would cover in a small video, small 10-15 minutes video. Okay, so this is almost everything for the first chapter. Okay, for the second chapter. Okay, that is stochastic processes. Thank you.